Alright, so now let's verify those offsets. So let's go ahead and restart our FTP while we're here. Get that error, so let's remember to get rid of that FTP daemon.dat. So delete that. Again, if that doesn't, you don't get that error, you don't need to do that. So let's restart again. Next time I'll just remember to do that. Play. Lightning bolt. We're running. Alright, so let's come over to Kali again and open up our war FTP scale.py. Again, let's comment out buffer equals our pattern and recreate buffer and set it equal to, let's say, A times 485. Remember that that is our offset to EIP. So plus B times 4, so that should be 4 bytes for EIP. Remember there were 4 extra bytes for the calling convention for some argument that will be ripped off when program returns. So C times 4 for that argument. And then I'm not very good at arithmetic, so typically what I do is do buffer plus equals, so that's going to append to buffer. So I want D times 1100 minus the length, so len of buffer. So buffer is going to be 485 plus 4 plus 4. So we want the total string length to be 1100, and you don't necessarily have to have it be just as long. I generally, once I find something that does work, I stick to it. Why, add more possibilities of things changing. So I found 1100 worked. So you might have a question, how did we know 1100 characters worked? And that was absolutely a good question. We will in the absolute next, the next one. Our next example, we will look at something called fuzzing that will allow us to find crashes in the first place. But for this one, kind of like when we did our MSO 8067, when we first learned Metasploit, I said, just believe me that this vulnerability is there. And sure enough, we found it using vulnerability scanners, using the check function, and other methods that we used for vulnerability discovery. It was indeed there. Same thing here. I'm just telling you, 1100 characters does it, and we'll stick with that. Again, we will do fuzzing next and see finding a crash in the first place. Alright, so we still get the length 1100, so we're just padding it out with D's. So what we expect to see is B times 4, so 42, 42, 42, 42 in EIP, and then we should see 4 bytes of padding, and then at ESP we should see the beginning of our D's, and again that's where we've chosen to put our shellcode. We have 607 characters to work with, so some of this 1100 characters is not showing up, or maybe it is. Maybe that's what's left is 607. See, I'm not very good at arithmetic. Yeah, that looks about right. Yeah, 607. So it looks like, yeah. Okay. This is why I just let it do the arithmetic for me. My arithmetic, again, is not that great. So that's the only change we need to make there. Make sure we do plus equals here in the second line. So it is going to append. If we just do an equals, all you'll get is some D's, and it probably won't crash at all. Alright, now go ahead and run it. Again, this is just verifying our offsets, so pop back over to XP, and sure enough, we get access violation when executing 42, 42, 42, 42. We come to our registers, we see it, and we should automatically be following ESP in the stack, but we can right-click on a register and say follow in stack, and that should be the beginning of our D's. So if we go up one, sure enough, here's our C's, here's our B's. So ESP is pointing at the beginning of our D's. So if we put our shellcode there, it will, if we can get to ESP, of course, it will send us to the beginning of those D's or our shellcode, and we can execute from there. We don't have data execution prevention on. We can execute off the stack just fine. So of course our next question is, how do we get to ESP? I got a little bit ahead of myself there. I'm like, oh, we can just go to ESP, but how do we get to ESP? Well, can we just hard code the address in? Generally, that's a pretty bad idea. It may move around, particularly between platforms. It's not always going to be in the same place. So anything that we hard code like that may possibly move will make our exploit more unstable. We like it to be as universal and stable as possible. So that's generally a bad idea. Plus with this one, we have another problem. Looks like ESP is at 00AFFD48. 00 is the null byte, and it turns out that in many cases the null byte is a bad character. It does represent the termination of a string, so if what you're working with is being used as a string by the program, so if it is calculating that to be a string, if it sees a null byte, it will say, okay, that's the end of the string, and everything that comes after will just be dropped off. So since our EIP overwrite is 485 bytes in, then that null byte would be at the end when we turn it into little Indian. So everything after EIP would disappear, so all of our nice Ds that we're going to use for shellcode wouldn't be there anymore, so we actually don't have the option to hard code this in anyways. Again, you're kind of taking my word for it that null byte is a bad character. It isn't always a bad character, not necessarily. You're always going to have a string. In this case, since it's the username, chances are it's going to be a string, but it's certainly possible that you'll run into exploits where it's not a string and the null byte will be just fine, or you may find some instances where you are forced to use a null byte and then you just lose everything after it, and hopefully you're still able to exploit it. You'll see lots of things if you continue in exploit development, but it is a bad character here. There's actually a couple more bad characters. So the bad characters for this one are null, 0A, and 0D, which are part of our enter, so our \r and \n. And then finally there is a fourth one. I was a bit confused when I first saw this one. 40 in hex is the @ symbol. If you look at man ASCII, you can see that. It's like, why the @ symbol? But as it turns out, since this is a username in FTP, the actual specification for it is username @server. So if I have an @ symbol in my username, it gets a little confused because it's like, okay, this is a server, but then there's an @ in there. So it's just part of the specification. I mean, that's really the key to bad characters, is you have to follow the specification for whatever protocol you're using and however it's being interpreted by the underlying program. So your bad characters are mainly going to vary based on what it expects to see, what it's capable of processing. So in this case, 40 is also a bad character because it is an FTP username. So, I mean, 0, 0, and 0A, 0D are pretty common. The 40, I see that a bit less. Usually an @ symbol is fine, but in this case it's not. Alright, so if we can't just hard code in our ESP is where to jump to, how are we going to get there? Well, I guess I kind of gave it away. We can jump there. So if we don't know much assembly, we may not be aware of it, but there is a command called JMP, short for jump. There's also call, which pretty much does the same thing, at least for our purposes. But Mona makes it pretty simple. We can just do a Mona. So if we do Mona JMP, that will find all the jumps and the equivalents as well. So calls, you could also do like, what can we do? We could do push ESP, so push ESP onto the stack, and then return, which return will grab whatever the top of the stack is and then return to it or send execution to it. So we could just do Mona jump -R for the register, and in our case we want to get to ESP. We can also tell it to automatically delete any bad characters. We can also do this manually on site. Whoops. But let's just go ahead and tell it to take the bad characters out, so it'll automatically throw out any pointers that have a bad character in them. So not -B, -CPB rather. I always get that wrong. I don't know why. I always want to say CBP. but it's CPB, so bad is last, to tell it to get rid of the bad characters. So Mona jump JMP -R for the register, ESP in our case, and -CPB, and then our bad characters we want to avoid. So we put those down here at the bottom. Let that execute. So it, again, it's going to take a minute because it is searching through all of our loaded modules for jump ESPs and equivalents. That was pretty fast. So if we come over here to clogs war-ftpd, now we have jump.txt. See our modules up here at the top again. So here are all of our pointers. So we have jump ESPs, call ESPs, push ESPs, and then return. So it finds the equivalents as well, and it did automatically take out all of our bad characters, so technically we can use anything on this list. Again, I like to, just for portability's sake, if I can, use the war FTP module itself or some of its DLLs. It only has one DLL, this mfc42.dll. I'm not going to be able to use anything in war FTP itself because it is loaded with a null byte, so every pointer in there is going to have a null byte in it, which we want to avoid, so everything got thrown out there. It looks like our MFC, it doesn't seem like they're in there anywhere, so it doesn't look like there's a jump ESP equivalent in there, at least not one that doesn't have a bad character. So let's see, it doesn't have a null byte, maybe it does, it doesn't look like it, no. But for whatever reason, they're not in there. So what we can do is choose another one. Again, in this case, you can use anything on this list. I like to use the MSV CRT. So here's MSV CRT DLL right here. So I'll just grab this one. So it's a push ESP and then a return. So it's an equivalent to jump ESP that Mona found. So again, you can use anything on this list as long as you automatically filter out the bad characters. You don't necessarily have to do the same one that I do. I'll just copy this and put it in my little notepad. Alright, so let's go ahead and restart. It is still crashed. So if we come over to immunity, let's get rid of that ftp.dat or ftpdaemon.dat. And then if we go to debug and restart, should open up by itself now. Sure enough, it does. With the lightning bolt. And if we come over to our Kali, now what I want to do, instead of b times 4 here, I'm going to put my jump ESP equivalent. I just pasted it in there for reference. I need to put it in little Indian format and tell Python that it's hex. So I need the 59 first. So again, byte by byte, turn it around. So 59 first, then 54, then C3, and then 77. And if yours is different, just make sure it's in little Indian format. So flip it around byte by byte. And put that in the place of our EIP overwrite, so in the place of our 42s or our b times 4. That's the only change we need to make right now. So let's go ahead and save this. And one more thing before we run it, I want to, like we did in the Linux example, actually set a breakpoint. So what we can do for that is just say BP for breakpoint, and then paste in. That didn't work out too well. Paste in that address. So BP and then alright, that's still not working. One more time. Edit, copy. Really? Okay. Alright, so I'll just write it in, because for whatever reason immunity doesn't want to take it from me. Alright, so let's make this smaller so I can see it. 77C3 5459. 77C35459. Alright, so we're going to set a breakpoint there and hit enter. And we can see our breakpoints if we go to view and then breakpoints. So there's the address, the module MSVCRT, it's always active, and it is a push ESP. Remember, this one is a push ESP and then return. It's actually 2 commands to do the equivalent of jump ESP. Alright, so let's go ahead and run it. So everything is as expected over here on Kali. We hop back over to XP. We are paused, but we don't have a crash. If we look at EIP, it is pointing to our 77C35459 in my case, so in MSVCRT. So we are at a breakpoint. If we look at the CPU, we do see our push ESP followed by a return. So we could let it play, or what we can do is we can hit F7. If you're on a Mac, you may have to hit function F7, and that will just execute one instruction at a time. So if I do F7, do push ESP, we take a look at our stack, we now have ESP pushed onto the stack, and then we return, so that's going to take that address and then try and execute what's there. So we do that return. So again, let's do function F7 if you're on a Mac, just F7 on Windows, and that indeed does redirect us to the beginning of our Ds. If we go up any, it tries to take those Ds as it grabbed that null in front of it, and now it thinks that that's another command. But so it takes us to ESP, so the beginning of our Ds. So now, of course, we need to replace our Ds with something useful. It looks like 44 in hex is just increment ESP. So we see a long list of increment ESP, so that's not going to be particularly useful in terms of shellcode. So certainly we can use MSF Venom and take advantage of that Metasploit payload system and create some shellcode that'll be more useful for us.